What's up, everyone? Today we're going to do some math for fun, which are actually about number theory. And here are the two problems that we're going to do. And in fact, these two problems are actually quite basic in number theory problems. So let's take a look. First, we would like to prove that n cubed minus n is a multiple of 6. And then in the second problem, we're going to show that 24 divides 5 to the 2n power minus 1. And of course, in both problems, we assume that n is an integer. Now, suppose we have never taken any number theory course and don't know any tools that are used in number theory. Let's see how we can figure out the proofs for these two problems. Here we go. Alright, so let's start with the first problem. It says n cubed minus n is a multiple of 6. So, even though we want to prove the statement is true, we know that there are many ways of proving, so I'll just pick one way that is easy for everyone to understand, including middle school and high school students that can understand the proof easily to show the statement is true. So we're going to start off with this. Since we want to prove this expression is a multiple of 6, let's try to figure out what we can do to the expression here. So consider the expression which says n cubed minus n. Since we want to show that it's a multiple of some number, the best way to figure out is, of course, trying to make it into some products. And then we will figure out what we can do in each part of the product and try to set up in cases. Then we get the following. N cubed minus n is equal to n times n squared minus 1. Of course, we factor out the n. And now we can also factor out the second part. So let's do it one more time. We get n times n minus 1 times n plus 1. Okay, great. And let's rearrange the order a little bit in an increasing order. So I'll put n minus 1 first, then times n plus 1. Excellent. So what can we do next? Well, we can write 6 as the product 2 times 3. Or in fact, we can write as 1 times 2 times 3, where the 1 doesn't really matter. Now, we want to show that this expression, n cubed minus n, which can be written as the following form, is a multiple of 6. Then, in other words, we want to show that it has to be a multiple of 2 and a multiple of 3 at the same time, so that it will be a multiple of 6. This is what we can do. We consider 3 cases. Case 1. Suppose n Alright, so since we want to show the expression which is equal to this part right here in product is a multiple of 6, which is the same as 2 times 3, we can show it by proving that this expression here is a multiple of 2 and a multiple of 3 at the same time. How can we do it? Well, let's check. To show that it has to be a multiple of 2, we can consider this case. Well, we can consider it in this way. So let's say case 1. If n is even, then we can see that the product is also even. Because now we can rewrite n as 2 times some integer k, implying the expression n cubed minus n, which is same as n minus 1 times n plus 1 is the same as, we're going to substitute it to get 2k minus 1 times 2k times 2k plus 1. Nice. And recall that k is an integer. We know that 2k minus 1 is an integer, k is an integer, 2k plus 1 is also an integer. It means that this whole thing is equal to 2 times some big integers. And let me write out that integer part, even though we don't care anymore. But that means it's a multiple of 2 here. Good. So we just show that what happens when n is even. So for case 2, if n is odd, then we can rewrite n as 2k plus 1, which implies that the expression n cubed minus n, or if we try to rewrite it as product, we can do the substitution quickly to get 2k plus 1 minus 1 times 2k plus 1 times 2k plus 1 plus 1 plus 1. And if we simplify the expression, we get 2k times 2k plus 1 times 2k plus 2. And again, since k here is an integer, we have 2 times product of all those integers, which is also an integer, implying that the expression n cubed minus n is even. Good. So we just check that this here is always even. In other words, it is a multiple of 2. Multiple of 2. Great. So we just need to finish up the proof by checking if the expression is always a multiple of 3. And this is what we're going to do. This time we're going to set up 3 cases. Case 1, if n is a multiple of 3, which means 3k for k an integer. Then we also have the other 2 cases. If n is not a multiple of 3, but it has a remainder 1. And finally, if n is not a multiple of 3, but have a remainder 2 here, then we can see that for the first case, we can say that the expression is a product of n times some other integers, which is a multiple of 3, because we just substituted, seeing that 3 is actually in part of the expression, and we are having 3 multiplied with other integers. Good. Similarly, in case 2, if we substitute in, we get the middle term here, n minus 1, which is the same as 3k plus 1 minus 1. And if we simplify it, this whole thing is turning out into 3k. It's also a multiple of 3 because now we see that is 3k times some other integers, meaning that it is it's divisible by 3 here. Great. And finally, with the similar argument, we can show that when n is equal to 3k plus 2, the expression n cubed minus n is also a multiple of 3. As we substitute into the last term, we get 3k plus 2 plus 1, which gives us 3k plus 3, and we can factor out the 3 and get 3 times the quantity k plus 1. Meaning this is also a product with a 3 here, and it's a multiple of 3. So we also show that no matter what n we choose, the expression n cubed minus n is always a multiple of 3. Great. So since we already showed that it's always a multiple of 2 and a multiple of 3, we can claim that is always a multiple of 6. And that's the end of the proof. Excellent. So let's move on to the second example. So let's move on to the second problem. All right. So in the second problem, we want to show that 24 divides 5 to the 2n power minus 1, which is equivalent to say that the expression 5 to the 2n power minus 1 is a multiple of 24. So they just mean the same thing. We're trying to play around with the words and trying to make it sound fancy, but it just means the exact same meaning. So what can we do? Well, this time we are going to do the proof by separating into 2 cases. So here we go. First, I'll set case 1. In case 1, I'll say let n equals 1. And why would I do this? Well, once we move on to the second case, you will see why I will separate out n equals 1 case as an individual. So let's see what we will get. If n equals 1, then the expression 5 to the 2n power minus 1 is equal to 5 to the 2 times 1 power minus 1. And 2 times 1 is clearly 2, which gives us 5 squared, which is 25, minus 1 is 24. And of course, 24 is always a multiple of 24 itself. So check. We already finished case 1. But now let's move on to the second case. Case 2. Suppose n is greater than or equal to 2 now. In this case, we're not using the proof of induction, but what we're going to do is we're going to use a very powerful tool, which is called the geometric sum or geometric series, if you have remembered, which says the following. If we have a polynomial, well, if we have a binomial with the following expression, a to the n power minus b to the n power, with the condition n has to be greater than or equal to 2, so it will not work when n is equal to 1. Then what we will get is this, we can factor out into a minus b times, now we want to get the other part of the polynomial, which is a to the n minus first power plus a to the n minus second power times b plus a to the n minus third power b squared plus all the way down to the last term, which only contains b here, and we see that the power has to be one less than it, which is b to the n minus first power, like this. Good. So using this tool right here, we'll be able to show that if n is greater than 2, we get the expression is divisible by 24. Why? This is what we are going to do. So here we're going to substitute. We're going to call this a here be this expression, some part of this expression, 5 to the 2n power. And since we only want the n power here, it means that everything else will be the a. In other words, our a will be 5 to the second power, which is equal to 25. And at the same time, we also need to call b. Well, luckily, we have 1 here, and 1 is equal to 1 to n power for any positive integer n. So we get b is equal to 1 here. Then let's finish the proof. By substituting in, we get the expression 5 to the 2n power minus 1, which can be written as 5 squared to the n power minus 1 to the n power, so that we get the a and b respectively, is equal to the expression here, a minus b, where a is 5 squared, which is 25, minus b, which is 1 here, and then we're going to multiply with the other term, which is just some big integer. Okay, so we don't have to worry about what the exact value is anymore, but we know that since it's the sum of the product or the power of integers, meaning that each term must be an integer as well, so that the sum is also an integer. That gives us the first term can be reduced to 24 times some large values or integers. Good. Then we just show that this is a product of 24 and some integer values, meaning that this is a multiple of 24. And therefore, we just show that 5 to 2n power minus 1 is a multiple of 24 for n is greater than or equal to 2 in the second case. And if we combine with the first case, which shows that when n is equal to 1, the expression is also a multiple of 24, we can conclude that 5 to the 2n power minus 1 is a multiple of 24 for n is a positive integer. Good. Which means 24 divides the expression 5 to the 2n minus 1. And that's it. We just finished another proof. So, of course, there are some tools that we can learn and use to make the proofs a lot faster, especially for the first problem. In this problem, we just use something that is quite straightforward already and not too long to finish the proof itself. But for the first problem, we can actually use some number theory tool that can make our proof a lot shorter and faster to finish the proof of the statement. So in the next video, I'm going to introduce the tool that we didn't use for problem 1. And that's it for today's video. If you enjoyed this video, please don't forget to like. And if you have any thoughts, please leave your comments below. If you think this video is cool and inspire you somehow, don't forget to share to your friends and trying to let them learn something from this video too. So I'll see you guys next time.